The first humans on Mars will not die from the landing. They will not die from the cold or the radiation or the thin and poisonous air. If they die, they will die from something quieter. A seal that cracks 2 months after touchdown. A water extraction pump that jams and cannot be replaced for 26 months. A filter clogged with toxic dust that nobody on Earth can fix in time. The landing will take 7 minutes. The first year will take 340 Martian days of building, repairing, rationing, and hoping that machines designed on Earth still work on a planet that wants them dead. Survival on Mars is not a single event. It is a slow argument with a world that never agreed to keep you alive. If you want to understand why surviving Mars may be harder than reaching it, hit that like button and subscribe. Now, let's begin. The spacecraft hits the upper Martian atmosphere at approximately 20,000 kilometers per hour. There is no runway, there is no ocean to splash down in, there is barely any air. The atmosphere of Mars is less than 1% the density of Earth's, a wisp of carbon dioxide so thin it might as well not exist, except it does exist just enough to set everything on fire. This is the paradox that has haunted mission designers for decades. Mars has too much atmosphere to ignore and too little atmosphere to use. On the Moon, there is no air at all. Landers fire their engines, slow down, and touch the surface. Simple, brutal, proven. On Earth, the atmosphere is thick and generous. Capsules and shuttles can use friction and parachutes to scrub off speed before landing. Mars offers neither option cleanly. The air is dense enough to generate searing heat during entry. Temperatures exceeding 1,400 degrees Celsius on the heat shield, but it is too thin to slow a heavy spacecraft to survivable landing speeds using parachutes alone. Every robotic mission the United States has ever successfully landed on Mars weighed less than 1 metric ton at touchdown. Viking 1 arrived in 1976 at roughly 600 kilograms. The Spirit and Opportunity rovers each weighed roughly 185 kilograms. Curiosity came in at approximately 900 kilograms. The heaviest object landed on Mars at the time, and it required a descent system so complex that engineers called it 7 minutes of terror. A heat shield, a supersonic parachute, a rocket-powered sky crane that lowered the rover on nylon cables and then flew itself away to crash at a safe distance. That system worked. Once. For 900 kilograms. A human mission to Mars would need to land somewhere between 40 and 80 metric tons of payload on the surface. That is not twice the challenge. It is not 10 times the challenge. It is a full 2 orders of magnitude beyond anything humanity has ever attempted on another planet. It is the difference between carrying a backpack across a river and driving a loaded freight train across the same river on a bridge that has not been built yet. And here is the number that should unsettle anyone who has followed this problem closely. NASA's own engineering assessments estimate only an 87% probability of successfully landing a payload exceeding 10 metric tons on Mars. That sounds reassuring until you turn it around. It means roughly 1 in 8 attempts would fail. 1 in 8. With human beings strapped inside, with no abort system during the final phase of descent, with no rescue vehicle waiting on the ground below, the history of Mars landings reinforces this discomfort. Across all nations, roughly half of all attempted Mars landings have failed. The Soviet Mars 3 lander reached the surface in 1971 and transmitted for approximately 14 seconds before going silent forever. The European Space Agency's Schiaparelli lander crashed in 2016 after its computer mistakenly concluded it had already reached the ground while still nearly 4 kilometers above the surface. Mars has a graveyard of machines that arrived but did not survive the landing. The physics behind this difficulty is unforgiving. A heavier vehicle enters the atmosphere with a higher ballistic coefficient, meaning it punches deeper into the thin Martian air before drag begins to slow it down. That leaves less time and less altitude for deceleration. Parachutes that worked for Curiosity cannot scale to human payloads. A parachute large enough to slow 40 metric tons in 1% of Earth's atmospheric density would need to be so enormous that no material currently in production could survive the deployment forces. Supersonic retropropulsion, the technique of firing rocket engines directly against the direction of travel while still moving faster than the speed of sound, is the leading candidate for slowing a crewed lander. SpaceX has demonstrated supersonic retropropulsion during Falcon 9 booster landings on Earth. But Earth has thick air and strong gravity. Mars has weak gravity and almost no air. The aerodynamics are fundamentally different. No supersonic retropropulsion system has ever been tested in the actual Martian atmosphere, and this is the detail that separates human Mars landing from everything that came before it. There is no Earth-based test environment that fully replicates Mars entry, descent, and landing. The atmospheric pressure is wrong. The temperature profile is wrong. The gas composition is wrong. The gravity is wrong. The wind patterns, the dust loading, the surface terrain, all different in ways that matter. Engineers cannot build a test chamber on Earth that simultaneously reproduces every variable a lander will experience descending through Martian skies. A test-as-you-fly philosophy, the gold standard in aerospace engineering, is simply not possible for Mars entry, descent, and landing. Every heat shield, every engine sequence, every guidance algorithm will be proven for the first time under real conditions with a crew aboard. The crew will feel the deceleration slam through their bodies as the atmosphere grabs the vehicle. They will feel the heat shield absorbing energy that would vaporize unprotected metal. They will hear the structure groan under aerodynamic forces no simulation can perfectly replicate. They will feel the engines ignite for retropropulsion, or the parachutes deploy depending on the architecture selected. They will feel the final seconds of powered descent as the guidance system searches for a flat patch on terrain mapped from orbit but never inspected from the ground. They will feel the landing legs hit Martian soil, and then silence. The engines stop. The dust cloud drifts away on wind so faint it barely moves the finest particles. The vibration ceases. For the first time in 7 months of interplanetary transit and 7 minutes of controlled violence, nothing is happening. That silence is where the real mission begins. Because now the crew is on Mars, and Mars does not care that they arrived. The planet offers no welcome, no breathable air, no drinkable water, no warmth. The surface temperature outside the lander may be minus 60 degrees Celsius at midday near the equator, plunging to minus 100 or colder after sunset. The atmospheric pressure at the surface is approximately 600 pascals, less than 1% of sea level pressure on Earth. At that pressure, exposed liquid water boils instantly. Exposed human blood does the same. Step outside without a pressurized suit, and consciousness lasts perhaps 10 to 15 seconds. Death follows, within a minute or two, not from suffocation, though that would come, but from the explosive depressurization of body fluids in a near vacuum. The crew does not step outside, not yet. The first task after landing is not exploration. It is not planting a flag. It is confirming that the thin shell of engineered metal and polymer surrounding them can keep them alive for the next 60 minutes. The habitat must be pressurized. In the most likely mission architecture, the crew lands near a habitat module that arrived on an earlier cargo flight, launched approximately 26 months before the crew departed Earth. This pre-deployed habitat was supposed to land autonomously, inflate or rigidize its pressure shell, activate its life support systems, and begin operating with no human presence. The crew is counting on finding a functioning outpost waiting for them on the surface. The pressure check is the first gate. Every seal, every joint, every viewport, every airlock gasket, every pass-through for electrical and fluid lines must hold atmosphere against the near vacuum outside. A pressurized habitat on Mars is not a building. It is a spacecraft that never flies. It must maintain an internal atmosphere at roughly 70 kilopascals, more than 100 times the ambient Martian pressure, continuously without interruption for years. A micro crack in a seal that leaks slowly is in some ways more dangerous than a sudden blowout, because the crew might not notice the atmospheric thinning until hypoxia begins to impair their judgment, which is the exact moment when good judgment matters most. On the International Space Station, small pressure leaks have occurred multiple times. In 2020, a leak in the Russian Zvezda module persisted for months before its exact source was identified. In low Earth orbit, that leak was manageable because resupply spacecraft arrived regularly and the crew could retreat to their Soyuz capsule and return to Earth within hours if necessary. On Mars, there is no Soyuz. There is no capsule standing by for emergency return. If the habitat loses pressure and the crew cannot find and seal the leak, they are confined to their landing vehicle, a smaller space with far fewer resources, while they attempt repairs with whatever tools and patch materials they have on hand. Power comes next. Without it, nothing else matters. The habitat's life support draws continuous electricity. The oxygen system needs power. The water system needs power. Heating needs power. Communications need power. Every critical function aboard the settlement runs on electrical energy generated by systems that were either pre-deployed and have been running unattended for over a year, or arrived with the crew and must be activated now, in the first hours, before battery reserves deplete. The crew's first power-related task is confirmation, not construction. If the mission architecture called for pre-deployed nuclear reactors or solar arrays, those systems should already be operating. Telemetry from Earth should have confirmed power generation during the months the cargo waited alone on the surface. But telemetry confirmation and physical confirmation are different things. A reactor that reported nominal output for 14 months might have developed a cooling system fault that telemetry did not capture. A solar array that reported stable voltage might have accumulated enough dust that its actual output has dropped below the margin needed to run life support, alongside water extraction, alongside oxygen production simultaneously. The crew must walk the power infrastructure personally. They must inspect connections, verify output against independent measurements, confirm that distribution systems are routing electricity where the habitat needs it, and identify any degradation that occurred during the months of autonomous operation. If the primary power system has failed or underperformed, the crew must diagnose the fault and determine whether it is repairable with the tools and spares available. If it is not repairable, they must calculate whether their backup power sources can sustain life support long enough to develop an alternative. This is not an abstract engineering exercise. It is a survival calculation performed under time pressure by people who landed on another planet within the last few hours. Every minute spent diagnosing a power anomaly is a minute drawing down battery reserves that cannot be recharged until the anomaly is resolved. The crew does not have days to troubleshoot. They may not have hours. Power is the heartbeat of the habitat. If it stops, everything stops. The crew activates communications. A radio signal from Mars to Earth travels at the speed of light, but the distance between the two planets varies from roughly 55 million kilometers at closest approach to more than 400 million kilometers when they are on opposite sides of the Sun. That translates to a one-way communication delay of between 3 and 22 minutes. The crew transmits a landing confirmation. Then they wait. 3 minutes, 10 minutes, 22 minutes, then the same delay for the response to come back. A single question and answer exchange can take 44 minutes. There is no real-time conversation with mission control. No one on Earth can watch a problem unfold and call out instructions as it happens. No flight controller can say, "Try the backup valve now," while the crew is standing in front of the panel. Every decision during the first hours is made by the crew alone, guided by procedures written months or years earlier by engineers who could not have known exactly what Mars would do to their hardware. This is the fundamental difference between Mars and every other crewed destination in spaceflight history. During the Apollo missions, communication delay to the Moon was approximately 1.3 seconds each way. Mission control could respond in near real time. Astronauts could ask a question and receive an answer within 3 seconds. During emergencies like the Apollo 13 oxygen tank explosion, the crew and ground worked together in something close to a live conversation, iterating on solutions, testing ideas, coordinating actions second by second. That kind of collaboration is physically impossible on Mars. Now consider the cargo problem. The pre-positioned habitat and equipment arrived on Mars months before the crew. Robotic systems reported telemetry back to Earth throughout the waiting period. Controllers monitored pressure readings, power output, temperature logs, and mechanical status indicators. But telemetry is a filtered version of reality. It tells you what the sensors are reading, not what the sensors are missing. A cargo habitat might report nominal pressure, while a hairline crack develops in a section where no pressure sensor was installed. A reactor might show stable output, while its heat rejection radiator gradually accumulates a film of electrostatic Martian dust that will cause overheating in 6 months. A water drilling rig might report successful ice extraction while actually pulling up perchlorate-saturated brine that will corrode its internal plumbing within weeks. The crew must verify all of this personally. They must inspect every system that's been running unattended, confirm every reading with direct observation, and test every mechanism that a robot could not test. They must do this quickly, because their consumables are finite, but thoroughly, because a system accepted as working and later found failing could cascade into a crisis when the crew has no margin to fall back on, and they must land close enough to the pre-positioned cargo to reach it. Precision landing on Mars is extraordinarily difficult. Curiosity's landing ellipse, the area within which the rover was expected to touch down, measured approximately 20 by 7 kilometers. That was considered a triumph of precision, but a human mission that must land within walking distance of pre-positioned cargo needs landing accuracy measured in tens of meters, not tens of kilometers. That represents a roughly 3 order of magnitude improvement in precision over the most accurate robotic Mars landing achieved to date, and an even larger leap when measured against the overall history of Mars landings. If the crew lands too far from the cargo habitat, they face an immediate logistics problem. They must drive or walk across unfamiliar Martian terrain in pressurized suits with limited range to reach their outpost. Every minute spent in transit is a minute drawing down suit consumables, a minute exposed to surface radiation, a minute during which a suit malfunction could be fatal. The first night on Mars arrives quietly. The sun, appearing roughly 2/3 the size it does from Earth, a smaller and dimmer disk, drops below the horizon. The Martian sky near the setting sun turns an eerie blue while the overhead sky fades from butterscotch to black. Without atmospheric density to trap warmth, the surface temperature plunges 40 degrees, 50 degrees. By midnight, the ground outside may be minus 90 degrees Celsius or colder. The habitat's thermal control system compensates continuously, drawing power from the reactor to maintain livable temperatures inside. The crew runs their first complete systems review. Pressure, holding. Temperature, stable. Oxygen, nominal. Carbon dioxide scrubbers, functioning. Water reserves, sufficient for now. Communications, operational with expected delay. Power output, steady. Everything is working. Every number matches what the simulations predicted. And that should concern them, because the simulations were built from models. The models were built from data collected by robotic missions that operated on Mars for a few years at most, with instruments designed to study geology, not to stress test human life support. The data is real but incomplete. Mars has not yet shown the crew what it does to human hardware over months and years of continuous operation. It has not yet tested every seal, with its fine, abrasive, electrostatically charged dust. It has not yet thrown a global dust storm that blankets the sky for 8 weeks. It has not yet demonstrated what perchlorate-laced soil does to airlock mechanisms and suit joints and filter membranes over hundreds of cycles. The first sol ends. Every system the crew depends on is now the newest, the freshest, the least degraded version of itself that it will ever be on Mars. From this moment forward, everything ages, everything wears. Every component moves one step closer to the failure that must be caught, diagnosed, and repaired before it compounds into something the crew cannot survive. The sun rises the next Martian morning, pale and distant, casting long shadows across a landscape that has never been touched by human hands. The crew has survived one sol. They have eaten their first meals on another planet. They have tried to sleep in gravity that feels wrong. 38% of Earth's, in air that smells of recycled metal and polymer, surrounded by a silence broken only by the hum of life support fans and the intermittent clicking of thermal expansion in the habitat walls. They are alive. The habitat held, the seals held, the reactor held, but they have not yet opened the airlock. They have not yet set foot on the surface. They have not yet begun the months of construction, installation, calibration, and relentless repair that will determine whether this habitat becomes a functioning settlement or the most expensive failure in human history. And somewhere beyond the thin Martian horizon, on a planet that is now between 55 million and 400 million kilometers away depending on orbital position, Earth is already assembling the next cargo shipment. But that ship will not launch for more than a year, and it will not arrive for 7 to 9 months after that. Until it does, the crew has exactly what they brought and exactly what the autonomous cargo flights delivered before them. Nothing more is coming. Not soon. Not quickly. Not in time to save them from whatever breaks next week, or next month, or during the first dust storm of the season. The first year has started, and everything the crew needs to survive it is already on Mars, already aging, already counting down toward the failure that will test whether this mission was designed well enough to absorb what this planet is about to do to it. The crew breathes in. The air inside the habitat tastes of recycled polymer and warm metal. It is clean, filtered, pressurized, and utterly finite. Every molecule of oxygen in this sealed shell was manufactured on Earth, compressed into tanks, loaded into a cargo vehicle, launched across interplanetary space, landed autonomously on Mars, and stored inside a pre-deployed habitat that waited months for the crew to arrive. Every breath the crew takes draws down a supply that Mars cannot naturally replenish. Earth's atmosphere is roughly 21% oxygen, maintained by photosynthesis across billions of plants, algae, and cyanobacteria operating in a biosphere that has been cycling gases for over 3 billion years. The Martian atmosphere is 95% carbon dioxide, with trace amounts of nitrogen and argon, and approximately 0.13% oxygen. You cannot breathe it. You cannot even crack a window to supplement what is inside. The habitat's air is the only air, and it will not last unless the crew begins making more. This is where MOXIE enters the story, not as a solution, but as a proof of concept that reveals the terrifying distance between demonstration and dependence. MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, rode aboard NASA's Perseverance rover and operated on Mars between April 2021 and August 2023. It was a device roughly the size of a car battery, weighing 15 kilograms. Its job was to prove that oxygen could be extracted from the Martian atmosphere by pulling in carbon dioxide, heating it to approximately 800 degrees Celsius inside a solid oxide electrolysis cell, and splitting the carbon dioxide molecules into carbon monoxide and oxygen. The oxygen was measured for purity and vented. The carbon monoxide was released back into the Martian air. MOXIE worked. Across 16 extraction runs over roughly 2.5 years, it produced a total of 122 grams of oxygen. At its most efficient, it generated 12 grams per hour at 98% purity or better. NASA called it a success, and it was. It proved that the chemistry functions on Mars, that the Martian atmosphere can feed an electrolysis cell, and that oxygen production on another planet is not a fantasy. But 122 grams of oxygen is what a small dog breathes in about 10 hours. A single human at rest consumes roughly 840 grams of oxygen per day. A crew of 4 would need more than 3 kilograms per day just for breathing, not counting oxygen consumed by other life support processes, not counting the vastly larger quantities needed for rocket propellant to fuel an eventual return to Earth. A human-scale oxygen production system would need to generate roughly 2 to 3 kilograms of oxygen per hour, sustained continuously over months, to both support the crew and begin stockpiling propellant oxidizer. That is roughly 200 times MOXIE's peak output, running not for an hour at a time, with long breaks in between, but around the clock, month after month, on a planet where the compressor intake might clog with dust, where thermal cycling between Martian day and night stresses every seal, and where a failure in the electrolysis stack does not mean a data gap in a rover experiment. It means the crew begins suffocating. No human-scale oxygen production system has ever operated on Mars. None has been built and tested at full scale on Earth under Martian atmospheric conditions. The technology readiness sits somewhere between proven principle and operational machine, which in engineering terms means years of development, testing, and validation remain. For the first crew, the oxygen system will be the newest, least proven, most critical piece of equipment on the planet. It will have been shipped from Earth, assembled or deployed either robotically or by the crew, and activated for the first time on a world where a failure cannot be answered with a phone call to the manufacturer. Water is the second crisis, slower but no less lethal. Mars has water. This is confirmed, measured, mapped, and increasingly well understood. The planet holds enormous reserves of water ice at its polar caps and extensive deposits of subsurface water ice across the mid-latitudes. NASA's Subsurface Water Ice Mapping Project, a multi-year effort integrating data from every orbital instrument capable of detecting buried ice, has produced refined maps showing where ice likely exists within meters of the surface in regions accessible to human missions. The Phoenix lander directly photographed water ice exposed by its landing thrusters in 2008. Radar instruments aboard the Mars Reconnaissance Orbiter have detected massive ice sheets buried beneath the plains of Utopia Planitia, estimated to hold as much water as Lake Superior. The water is there. The problem is getting it out. Martian water ice does not sit in convenient frozen lakes on the surface. It said, at the latitudes suitable for human landing sites, roughly between 30 and 50 degrees north or south, the ice is buried under a layer of dry regolith that may be anywhere from 1 to several meters deep. This overburden is a mixture of fine-grained basaltic dust, rocks, and perchlorate salts that must be drilled through or excavated before reaching the ice layer. The ice itself may not be a solid uniform slab. It could be mixed with regolith, forming a dirty ice matrix that requires heating, melting, and filtering before the water is usable. Honeybee Robotics has developed a concept called Red Water, an integrated drilling and water extraction system designed specifically for this challenge. The approach involves drilling through the overburden and into the ice layer, then injecting heat to melt the ice in place and pumping the resulting water to the surface. A method called a Rodriguez well, or Rodwell, adapted from techniques used at research stations in Antarctica. Testing on Earth has demonstrated that the system can penetrate simulated Martian regolith and extract water from subsurface ice. But testing in a laboratory under simulated conditions is not the same as operating on Mars. The drilling system must function in Martian gravity, which is 38% of Earth's, altering the dynamics of bit pressure and chip removal. It must operate in temperatures well below freezing, where lubricants behave differently and metal components become brittle. It must handle perchlorate-contaminated ice, which means the extracted water must be filtered and purified before it can be used for drinking, for growing food, or as feedstock for producing hydrogen and oxygen through electrolysis. Perchlorate at the concentrations found in Martian soil is a potent thyroid disruptor. Consuming perchlorate-contaminated water over weeks or months could impair the crew's metabolic function, immune response, and cognitive performance. Exactly the systems they need functioning at peak capacity to keep the settlement running. The water system on Mars is not a faucet. It is an industrial mining, heating, pumping, filtering, and purifying operation that must run continuously in conditions where every component is imported and every replacement part is either already on the planet or 26 months away. Power governs everything. Without reliable electricity, there is no oxygen production, no water extraction, no heating, no life support, no communications. The habitat goes dark. The crew dies. NASA's selection of nuclear fission as the primary surface power source for initial human Mars missions reflects the hard reality that solar energy alone is insufficient. Solar panels on Mars produce roughly 43% of the power they would on Earth because Mars orbits farther from the Sun. Dust accumulation steadily degrades panel efficiency over time, and global dust storms, which occur on Mars roughly every 3 to 4 Martian years, can reduce incoming sunlight by 90% or more for weeks or months. The Opportunity rover operated successfully on Mars for nearly 15 years, an extraordinary feat. But in June 2018, a global dust storm engulfed the planet. Solar output to the rover's panels dropped so drastically that Opportunity could not generate enough power to keep its electronics warm. It entered a protective hibernation and never woke up. The storm killed a machine that had survived everything else Mars had thrown at it for a decade and a half. A crew cannot hibernate. They must eat, breathe, stay warm, and keep life support running through every dust storm, every night, every season. This is why nuclear power is not a luxury for Mars. It is a survival requirement. The fission surface power systems under development are designed to provide approximately 40 kilowatts of continuous electrical power from a reactor massing under 6 metric tons. The reactor uses enriched uranium fuel, generates heat through controlled fission, and converts that heat to electricity through a Brayton cycle power converter. It operates independently of sunlight, dust, weather, and time of day. In principle, it can run continuously for 10 years without refueling. In principle, on Earth, the Krusty demonstration in 2018 successfully operated a prototype kilopower reactor at full power for 28 hours under controlled conditions. It worked. The physics was validated. But Krusty was a subscale experiment generating roughly 1 kilowatt, not 40. It operated in a vacuum chamber, not on a planetary surface. It never endured dust infiltration, ground-transmitted vibration, autonomous startup without human oversight, or the thermal environment of a world where daytime surface temperatures might reach -20 degrees Celsius and nighttime temperatures drop below -90. A fission reactor on Mars must deploy from its shipping configuration, extend its heat rejection radiators, initialize its nuclear fuel, and begin generating stable power, either entirely autonomously or with minimal crew intervention. If it was pre-deployed on a cargo flight, it must have survived the landing, powered up without humans, and maintained operational status for more than a year before the crew arrives. If it arrives with the crew must assemble and activate it in the first days after landing while surviving on backup battery and solar power. Either way, the reactor has never operated on Mars before this moment. The crew is commissioning a nuclear power plant on an alien planet with no support infrastructure, no grid to tie into, no backup utility, and no option to call a technician. If the reactor fails to start, they are left dependent on solar panels that may or may not survive the next dust storm, producing power that may or may not be sufficient to run the oxygen and water systems simultaneously. Food enters the calculus with quiet urgency. The crew cannot grow enough food during the first year to sustain themselves. That is a flat statement based on current agricultural technology. No closed-loop bioregenerative life support system has ever produced 100% of a crew's caloric needs in any space mission or Earth-based analog. The International Space Station grows small quantities of lettuce and radishes for supplementary nutrition and crew morale. It does not grow meals. Growing food on Mars would require pressurized greenhouse modules with artificial lighting, heated water, nutrient-enriched growing media, and a carbon dioxide-oxygen exchange system linked to the main habitat. The soil outside is unusable as is because of perchlorate contamination and the absence of organic matter and microbial ecology. Any agriculture would be hydroponic or aeroponic, using cleaned water and imported or synthesized nutrients. Even under ideal conditions, the caloric yield of a small pressurized greenhouse would supplement the crew's diet, not replace it. The first crew eats prepackaged food, freeze-dried, thermostabilized, irradiated, and vacuum-sealed meals designed to remain nutritionally viable for years. These meals were prepared on Earth, loaded onto cargo flights, and stored on Mars for months before the crew arrived. They must remain edible and nutritious throughout the entire surface stay, which, under the most likely mission, architecture spans 500 or more Martian sols, roughly 18 Earth months. Caloric requirements for physically active crew members in partial gravity are not trivial. Estimates range from 2,500 to 3,000 calories per person per day. For a crew of 4 over 500 sols, that approaches 6 million calories of prepackaged food, every gram launched from Earth at staggering cost. Every meal consumed is a meal that cannot be replaced until the next resupply window. Rationing is the baseline plan, but the crew is not eating these carefully rationed meals as the healthy peak performance astronauts who left Earth 7 months ago. They are eating them as diminished versions of themselves, and this is a first-year problem that receives far less attention than dust or radiation, despite the fact that it shapes every operational decision the crew will make during the most physically demanding phase of the entire mission. The transit from Earth to Mars takes approximately 7 to 9 months. During that time, the crew lives in microgravity. Zero-G is not a benign environment. It is a slow and relentless destroyer of the human body. Without the constant downward pull that forces muscles to support weight and bones to bear load, the body begins dismantling itself. It does this efficiently, methodically, and without permission. Bone density decreases at a rate of roughly 1 to 1.5% per month in load-bearing bones, particularly the hips, spine, and legs. Over a 7-month transit, that translates to a 7 to 10% loss before the crew even touches Martian soil. On Earth, a 10% reduction in bone density would classify a middle-aged adult as having early osteopenia. The crew arrives on Mars with bones measurably weaker than when they departed, and those weakened bones must now bear weight again, carry equipment, absorb the impact of walking on uneven terrain in pressurized suits, and support bodies performing manual labor that no rover can do for them. Muscle atrophy is faster and more visible, Without gravitational loading, skeletal muscles begin losing mass within days. The calf muscles, the quadriceps, the muscles along the spine that hold the body upright, all of them degrade in microgravity, despite rigorous daily exercise countermeasures. Crew members aboard the International Space Station exercise roughly 2 hours per day using resistance machines and treadmills designed specifically to slow these losses. Even with that regimen, station crew members return to Earth measurably weaker than when they left. Some require weeks of rehabilitation before they can walk without assistance. The Mars transit vehicle will carry exercise equipment, but the constraints of mass, volume, and power aboard an interplanetary spacecraft are far more severe than on the station. The exercise hardware may be less capable. The crew's motivation to maintain a grueling daily workout during a monotonous 7-month coast phase may waver, and even the best exercise protocols cannot fully prevent deconditioning in the absence of gravity. The crew lands weaker than they have been since adolescence. Cardiovascular deconditioning adds another layer. In microgravity, the heart no longer pumps blood upward against gravity. It remodels, becoming smaller and rounder. Blood volume decreases as the body sheds fluid it no longer needs to maintain pressure against a gravitational gradient. When the crew lands on Mars and suddenly experiences 38% of Earth's gravity, their cardiovascular systems must readjust. Blood pools in the lower extremities, orthostatic intolerance, a tendency to feel dizzy or faint when standing, is common in astronauts returning to gravity. On Earth, the crew would be eased back into activity over days or weeks, with medical teams monitoring their blood pressure and heart rhythm. On Mars, the crew may need to begin habitat inspections, equipment deployment, and critical system checks within hours of landing. Vestibular disruption complicates everything further. The inner ear's balance system recalibrates in microgravity, and recalibrating again to a gravitational environment takes time. During the adjustment period, which can last days to weeks, crew members may experience spatial disorientation, nausea, and impaired coordination. These symptoms are not merely uncomfortable, they are operationally dangerous. A crew member who misjudges a step while carrying a heavy component across Martian regolith, or who becomes disoriented while performing a time-critical repair inside a suit with limited visibility, faces consequences that range from equipment damage to injury to death. The bitter irony of the first year is this: the most physically demanding period of the entire Mars mission arrives precisely when the crew is at their physical worst. The first weeks after landing require construction, assembly, deployment, inspection, calibration, and repair. They require lifting, carrying, climbing, bending, kneeling, and working in pressurized suits that resist every movement through the stiffness of their joints. They require sustained physical effort across multiple consecutive sols without the option of rest days, because the habitat must become operational before the crew's limited onboard consumables run out. And Mars does not compensate. 38% gravity reduces the load on bones and muscles compared to Earth, but it does not eliminate it. Equipment still has mass. Inertia still resists acceleration. A 50-kilogram component weighs the equivalent of 19 kilograms on Mars, but it still requires the same force to stop, turn, or lift overhead. A crew member who has lost 10% of their bone density and significant muscle mass must handle equipment that is lighter but not light, on terrain that is uneven and unfamiliar, in a suit that fights their every movement, while their cardiovascular system is still adjusting to the partial gravity it has not experienced for over half a year. Exercise protocols on Mars will aim to rebuild what the transit destroyed, but rebuilding takes months. During those months, the crew operates at reduced physical capacity while performing tasks that demand full capacity. Every extravehicular activity carries an elevated risk of injury. Every manual task takes longer and exhausts the crew more quickly than it would have before transit. Fatigue accumulates faster, recovery takes longer. The margin between operational performance and physical breakdown narrows during the exact period when the settlement can least afford to lose a crew member to an avoidable injury. No mission to Mars has ever carried a human crew through this transition. The closest analogue is astronaut rehabilitation after long-duration station missions, but those astronauts return to full Earth gravity with immediate medical support, physical therapy, and the option of rest. The Mars crew returns to partial gravity with no medical support beyond what they brought, no physical therapist, and no option to rest because the habitat will not build itself. The first crew on Mars will not only be building a world from spare parts, they will be building it with bodies that have been quietly disassembled by 7 months of weightlessness, on a schedule that does not account for the time it takes a human frame to remember how to carry its own weight. And now the most fundamental constraint reveals itself, the one that shapes everything about first-year survival on Mars: orbital mechanics. Earth and Mars do not orbit the Sun at the same speed. Earth completes one orbit in 365 days. Mars takes 687 days. Because of these different orbital periods, the two planets align favorably for transfer missions only once every approximately 780 days, or roughly 26 Earth months. This alignment is called the synodic period, and it is as fixed and unyielding as gravity itself. No engine, no spacecraft, no technology can change it. It is geometry. When the crew launches from Earth to Mars, they depart during a window that lasts roughly 3 to 4 weeks. If they miss the window, they wait 26 months for the next one. The transit to Mars takes approximately 7 to 9 months depending on the trajectory. After landing, the crew must remain on Mars until the next favourable alignment allows a return flight. Under a typical long-stay mission profile, the surface stay lasts approximately 500 days, roughly 16 to 18 months, before the return window opens. This means that from the moment the crew touches down on Mars, the earliest they could physically return to Earth is roughly 500 days later, and the return flight itself takes another 7 to 9 months. From landing to Earth arrival, the crew is committed to more than 2 years away from home. If something goes catastrophically wrong on Sol 10, on Sol 50, on Sol 200, there is no early flight home. There is no emergency shuttle. The planets are where they are, and the physics of orbital transfer does not accommodate human emergencies. But the resupply constraint is even more punishing than the return constraint. A cargo resupply mission launched from Earth during the next available window after the crew departs would not arrive at Mars until 7 to 9 months after launch. Depending on exactly when, during the synodic period, the crew lands, the next possible resupply delivery could be anywhere from 18 to 26 months away. If the crew discovers on Sol 30 that a critical component is failing, a component that was not included in the original manifest, because nobody predicted that particular failure mode, they cannot receive a replacement for nearly 2 years. This transforms every piece of equipment on Mars into a survival instrument. A broken wrench is not an inconvenience. A degraded filter is not a maintenance task to schedule for next quarter. A cracked valve housing is not a warranty claim. Every failure must be fixed with what exists on Mars at that moment, because nothing else is coming. Think of the communication delay and the resupply gap together, and a picture of profound isolation emerges. The crew radios Earth to report a problem. Mission Control receives it minutes later, consults engineers, analyzes telemetry, develops recommendations, and transmits a response that travels the same distance back. A complex troubleshooting session involving multiple back-and-forth exchanges might stretch over hours or even days, each cycle separated by the unbridgeable distance between two planets orbiting the same star at different speeds. Trying to solve a time-sensitive hardware failure through this communication channel is like trying to have a phone call where every sentence is sent by mail. You speak, you wait, you receive a reply that may not address what has happened in the intervening minutes, you clarify, you wait again. Meanwhile, the problem has not paused, the leak has not stopped, the temperature has not stabilized, the oxygen concentration has not held steady. Mars operates in real time. Earth's help arrives in delayed time. The gap between those two timelines is where emergencies become fatal. The crew must be capable of diagnosing and repairing every critical system aboard the habitat without real-time guidance from Earth. They must carry repair manuals, diagnostic tools, spare components, raw fabrication materials, and the skills to use all of it. They must be doctors, plumbers, electricians, chemists, miners, welders, programmers, and mechanics. Not metaphorically, literally. There is no specialist to call. There is no contractor to hire. There is no next-day delivery. The environmental control and life support system ties all of this together. It is not one machine. It is a network of interconnected subsystems that regulate atmospheric composition, remove carbon dioxide, manage humidity, control temperature, purify water, process waste, and monitor air quality continuously. On the International Space Station, the environmental control and life support system has been refined over more than 2 decades of continuous operation, and it still requires regular maintenance, component replacement, and occasional emergency intervention. The station receives resupply missions roughly every few months, and if a system proves unrepairable, the crew simply goes home. On Mars, the environmental control and life support system must function for the entire surface, stay with whatever spare parts were included in the manifest. If the carbon dioxide removal assembly fails, the crew must repair it or switch to a backup if a backup was included. If the water recovery system produces contaminated output, the crew must troubleshoot the contamination source while rationing clean water reserves. If humidity control fails in one module, condensation can accumulate on electronics, cause short circuits, promote microbial growth, and degrade air quality in ways that compound faster than the crew can respond. Every subsystem depends on every other subsystem. Oxygen production depends on power. Water extraction depends on power and mechanical drilling. Food preparation depends on water. Waste processing depends on water and power. Temperature control depends on power. Communications depend on power. If the reactor output drops by 30% during a dust storm's secondary effects, the crew must decide which systems to throttle back. Less power to heating means colder interior temperatures, which increases metabolic demand, which increases oxygen consumption, which increases the load on the oxygen production system, which draws more power. The feedback loops are vicious and they do not negotiate. By the end of the first month, the crew has activated every primary system. Oxygen production is running, but at a fraction of the rate needed for full self-sufficiency. Water extraction has begun, but the output must be filtered, tested, refiltered, and stored before it can be consumed. The reactor is producing power, but every kilowatt is allocated and none are spare. The food supply is finite and the rationing schedule is locked. The communication delay means every report to Earth is a monologue, and every response is an artifact of a conversation that happened 20 minutes in the past. The crew is building a world, but they are building it from spare parts shipped across interplanetary space, using tools designed for a planet that is not this planet, following procedures written by engineers who have never stood on Martian soil, and they are doing it on a clock that does not pause when things break. Nothing about this is routine yet. Nothing about this has been proven by years of operational experience. Nothing about this has a track record that tells the crew which components will last and which will fail first. They are the first humans to attempt sustained habitation on another planet, and every system surrounding them is exactly as untested as they are. The habitat hums, the fans circulate air, the filters catch dust, the reactor produces heat and electricity, the oxygen system splits carbon dioxide molecules one at a time, the water system melts frozen Martian ice and pushes it through purification membranes. The crew eats pre-packaged meals, exercises to slow bone and muscle loss in reduced gravity, runs diagnostic checks on equipment that has no service history, and waits for the next report from a home planet that grows more distant in the sky with each passing week as the two worlds drift apart in their separate orbits. Everything is working, for now, but Mars has not yet tested any of it. The first dust storm has not arrived, the first major equipment failure has not occurred, the first medical emergency has not happened. The first moment when two critical systems fail simultaneously and the crew must choose which one to save has not come. It will come. The planet guarantees it, and when it does, the crew will face it alone, with whatever they have, wherever they are, with no rescue closer than 250 days away at best. The slow war is about to begin. Mars does not attack with explosions or earthquakes or visible catastrophe. Mars attacks with dust. It starts with something too small to see. Individual Martian dust particles measure roughly 3 micrometers in diameter, smaller than a grain of talcum powder, smaller than a human red blood cell. This dust is not like desert sand on Earth, coarse and heavy, settling quickly when disturbed. Martian dust is so fine it behaves more like smoke. It hangs in the atmosphere for weeks after a storm. It drifts through openings that would stop any terrestrial particle. It clings to surfaces with electrostatic charge, bonding to metal, fabric, glass, and polymer, with a tenacity that simple brushing cannot overcome. And it is everywhere. Mars is a dust world. The entire surface is coated in a layer of regolith, composed of iron-rich basaltic fragments ground fine over billions of years by wind erosion, meteorite impacts, and thermal cycling. This dust is not benign sediment. It is chemically reactive, physically abrasive, and toxicologically dangerous in ways that make lunar dust look almost friendly by comparison. The chemical danger comes from perchlorates. These reactive chlorine-oxygen compounds have been detected at every Martian landing site where instruments were capable of measuring them. The Phoenix lander found perchlorate concentrations of roughly 0.4 to 0.6% by weight in the Arctic soil. The Curiosity rover confirmed perchlorate presence in Gale Crater near the equator. Analysis of data from multiple missions suggests perchlorates are globally distributed, not confined to specific regions, but spread across the Martian surface as a ubiquitous contaminant. On Earth, perchlorate is a regulated toxic substance used in solid rocket fuel and certain industrial processes, but controlled because of the damage it does to the thyroid and the cascade of hormonal disruption that follows. The United States Environmental Protection Agency sets advisory levels for perchlorate in drinking water at low parts per billion concentrations. But what makes perchlorate especially dangerous on Mars is not its presence in the soil, which the crew can learn to manage through water filtration. It is its presence in the air. Every dust particle that enters the habitat carries perchlorate into the one environment the crew cannot decontaminate without the filtration systems that are themselves degraded by the dust they must process. On Mars, the perchlorate concentration in surface soil is measured in parts per thousand. It is orders of magnitude higher than what is considered safe for human exposure on Earth, and this contaminated soil becomes airborne dust, the same dust that coats every surface, infiltrates every mechanism, and will inevitably find its way inside any habitat no matter how carefully the airlocks are designed. The crew will track dust inside on their suits every time they conduct an extravehicular activity. The suits will carry it in the folds of fabric, in the joints of gloves, in the treads of boots, in the helmet ring seals. Never airlock procedures can reduce the amount that enters the habitat, but no airlock protocol tested on Earth or aboard the International Space Station has ever dealt with dust this fine, this chemically hostile, or this electrostatically persistent. Apollo astronauts on the Moon reported that lunar dust infiltrated everything despite aggressive containment efforts. It scratched visors, jammed mechanisms, irritated eyes and lungs, and could not be fully removed from suits. Martian dust shares many of these physical properties and adds chemical toxicity on top. Once inside the habitat, perchlorate-laden dust settles on food preparation surfaces, contaminates water systems, enters the respiratory filtration loop, and accumulates in equipment interiors. The crew breathes it, not in visible clouds, but in trace quantities that build up over months. Long-term inhalation of fine particulate matter causes pulmonary inflammation on Earth, even when the particles carry no chemical payload. Add perchlorate and the respiratory risk compounds. Add the iron oxide-rich mineral composition of Martian dust, which some studies suggest may generate reactive oxygen species in lung tissue, and the picture worsens further. The physical damage is equally relentless. Martian dust is abrasive. It acts on exposed surfaces the way fine sandpaper acts on wood, except this sandpaper is applied by a planet and it never stops grinding. Suit visors degrade, solar panel coatings scratch, airlock seals wear, mechanical joints stiffen as dust works into bearing surfaces and actuator housings. Every extravehicular activity accelerates this damage, and extravehicular activities cannot be avoided because the crew must maintain exterior equipment, inspect systems, and operate surface hardware. The dust problem does not plateau, it worsens with time. Every sol adds another thin layer. Every wind event redistributes particles across the settlement. Every suit ingress brings another invisible cargo of contamination. The filtration systems designed to keep the habitat air clean must handle an increasing dust load as the months progress. Filters clog. Replacement filters are finite. When the last clean filter is installed, the crew must either fabricate replacements from available materials, clean and reuse degraded filters, or accept declining air quality. Then there is what the dust does from a distance. Mars experiences dust storms that range from localized events covering a few hundred kilometers to global phenomena that engulf the entire planet. Regional storms can form within days, driven by temperature differentials between sunlit and shadowed terrain. Global storms occur less frequently, roughly every 3 to 4 Martian years, but when they arrive, they can last for months. During a global storm, the sky darkens to twilight for weeks. Atmospheric opacity can climb so high that solar energy reaching the surface drops by more than 90%. Even with a nuclear reactor providing baseline power, the crew would lose any solar supplement they depend on for margin. Heating, water extraction, and oxygen production all compete for a power budget that just shrank without warning. Equipment that requires exterior access for maintenance becomes unreachable because visibility outside the habitat drops to meters. Dust accumulation rates spike, and every surface exposed to the storm collects another layer of abrasive, perchlorate-laden grit that must eventually be cleaned before the equipment can function normally again. The crew cannot wait the storm out passively. They must actively manage the power deficit, deciding in real time which systems to throttle back and which to protect, while the storm runs on its own schedule, indifferent to their calculations. Radiation is the invisible threat, the one the crew cannot see, cannot feel, and cannot fully escape. Earth is shielded by 2 powerful defenses against space radiation: a global magnetic field that deflects charged particles from the sun and from deep space, and a thick atmosphere that absorbs the particles that make it through. Together, these shields reduce the radiation dose at sea level to roughly 2.4 millisieverts per year from natural background sources. Mars has neither defense in comparable strength. The planet lost its global magnetic field billions of years ago as its core cooled, and the internal dynamo that generated the field ceased operating. What remains are scattered patches of residual crustal magnetism, too weak and too localized to provide meaningful protection. The Martian atmosphere, at less than 1% the density of Earth's, absorbs some incoming radiation but allows the most energetic particles to reach the surface largely unimpeded. 2 categories of radiation dominate the Martian surface environment. Galactic cosmic rays are high-energy particles, primarily protons and heavier atomic nuclei, that originate from supernova explosions and other violent events across the galaxy. They arrive continuously, from all directions, at energies so high that no practical amount of shielding can fully stop them. Some galactic cosmic ray particles carry enough energy that they penetrate meters of solid rock. They pass through spacecraft walls, through habitat structures, through the human body, depositing energy along their paths and breaking molecular bonds in biological tissue. The Radiation Assessment Detector aboard the Curiosity rover has measured the galactic cosmic ray dose equivalent on the Martian surface at approximately 0.67 millisieverts per day. Over the course of a year, that accumulates to roughly 245 millisieverts. For comparison, the annual occupational radiation exposure limit for nuclear industry workers on Earth is 20 millisieverts. A crew spending 1 year on the Martian surface would accumulate more than 12 times that limit from galactic cosmic rays alone, and a habitat's walls reduce, but do not eliminate this exposure because the most energetic particles penetrate virtually any practical shielding thickness. Solar particle events are the second threat. These are intense bursts of energetic protons ejected by the sun during solar flares and coronal mass ejections. Unlike galactic cosmic rays, which are constant and relatively predictable, solar particle events are sporadic and can arrive with little warning. A major event can deliver a radiation dose equivalent to months of galactic cosmic ray exposure in a matter of hours. On Earth, the magnetic field and atmosphere absorb most solar particle radiation. On Mars, a powerful solar particle event would blast the surface with a concentrated dose that could cause acute radiation symptoms in unshielded crew members: nausea, fatigue, vomiting, immune suppression, and in extreme cases, damage to the central nervous system. NASA's radiation exposure models, validated against data from the Artemis 1 mission and corroborated by measurements from Curiosity's detector, estimate that the total radiation dose during a round trip to Mars, including transit and surface stay, would reach approximately 600 to 1,000 millisieverts. That exceeds NASA's current career exposure limits for astronauts. The crew must manage this exposure without the option of simply going home when the dosimeter reads too high. Shielding strategies exist, but are limited. Water, polyethylene, and Martian regolith can reduce galactic cosmic ray doses if used as shielding material, but the reduction is modest because the highest energy particles penetrate nearly any material at practical thicknesses. Storm shelters, heavily shielded compartments within the habitat where the crew retreats during solar particle events, are essential but only protect against the acute bursts. They do nothing about the chronic daily galactic cosmic ray exposure that accumulates one fraction of a millisievert at a time every day for the entire surface stay. The biological consequences of this exposure are not fully understood. No human has ever been exposed to the Martian radiation environment for a sustained period. Studies from medical radiation therapy, nuclear accident survivors, and laboratory experiments indicate increased cancer risk, potential cardiovascular damage, possible cognitive impairment, and accelerated cataract formation. But the specific mix of particle types and energies on Mars differs from any terrestrial exposure scenario, making direct comparison difficult. The crew carries this risk silently. They do not feel the radiation, they do not see it. They might never experience acute symptoms during the surface stay, but the cumulative damage to their cells, the increased probability of cancer developing years after they return to Earth, the potential subtle degradation of cognitive function over the months of exposure, all of it accumulates without symptoms, without warning, without any treatment the crew can administer on Mars. Equipment does not care about perchlorates or radiation. Equipment cares about thermal cycling, mechanical stress, and time. Mars subjects every piece of hardware to a daily temperature swing that would destroy most consumer electronics within weeks. Surface temperatures at a mid-latitude landing site might reach minus 20 degrees Celsius during a summer afternoon and plunge to minus 90 degrees Celsius by the following dawn. That is a 70-degree swing, repeated every single sol, stressing every material, every bond, every joint. Metals expand and contract, polymers stiffen and crack, adhesives weaken, solder joints fatigue. O-ring seals that were pliable at installation become rigid and brittle after hundreds of thermal cycles. Electrical connectors develop intermittent contact as their housings warp imperceptibly. Hydraulic lines develop microfractures at stress concentration points. On Earth, engineers test equipment for thermal cycling, but the test protocols are limited. A typical qualification test might subject hardware to a few hundred cycles across the expected temperature range. On Mars, the equipment must survive thousands of cycles over a mission lasting 18 months or more. Every sol adds another cycle. Every cycle adds another increment of fatigue. The crew cannot inspect every component daily. They must rely on sensor data, diagnostic software, and visual inspections during scheduled maintenance. But sensors can fail. Software can miss subtle trends. Visual inspections cannot see inside sealed assemblies. The failure that matters most is almost always the one nobody anticipated. But the most insidious equipment failures during the first year may not be mechanical at all. They may be electronic. Every critical system in the Mars habitat is monitored, controlled, and regulated by computing hardware running software written on Earth. The environmental control system does not operate manually. Temperature regulation, atmospheric composition management, power distribution, communication scheduling, fault detection, all of these functions depend on processors, memory chips, circuit boards, and sensor arrays that were designed, tested, and qualified under terrestrial conditions. On Mars, those electronics face an environment they were never truly qualified for. Galactic cosmic rays do not merely threaten human tissue, they also damage semiconductor materials. When a high-energy particle strikes a microprocessor, it can flip a bit in memory, corrupt a software instruction, trigger a false sensor reading, or in rare but documented cases, permanently damage a transistor gate. These events are called single-event effects, and they occur with measurable frequency in any radiation environment above Earth's protective magnetosphere. Spacecraft electronics are designed with radiation hardening, techniques that make circuits more resistant to single-event effects. But radiation-hardened components are expensive, heavy, and often a generation behind commercial processors in computational capability. The Mars habitat will contain a mixture of fully hardened flight computers and partially hardened or commercial-grade electronics used for secondary systems, instrumentation, and data logging. The less hardened components will be more vulnerable. Over months of continuous operation, radiation-induced errors accumulate. A single bit flip in a temperature sensor's calibration register might cause the environmental control system to read interior temperatures as 2 degrees warmer than they actually are. The system responds by reducing heating output. The habitat cools slightly. The crew feels colder, but attributes it to seasonal temperature changes outside. Weeks later, the discrepancy has compounded. The system is now heating insufficiently because its temperature reference has drifted. A crew member checks a backup thermometer and discovers the discrepancy. They recalibrate. But how many other sensors have drifted without a backup to catch them? Sensor drift is a quiet predator. On Earth, sensors are regularly calibrated against known references by qualified technicians using calibrated instruments. On Mars, the crew has whatever calibration references were included in the manifest. If a pressure sensor drifts low, the habitat might actually be at lower pressure than the control system reports. A slow leak could go undetected because the monitoring system believes the pressure is nominal. If an oxygen sensor drifts high, the system might reduce oxygen production because it believes atmospheric oxygen is sufficient, when in reality concentrations are falling. The crew cannot independently verify every sensor against every other sensor continuously. They must trust the instrumentation, and that trust is only justified if the instrumentation remains accurate over time in an environment that actively degrades its accuracy. Software watchdogs, error-correcting memory, and redundant sensor arrays all mitigate this risk, but they mitigate it imperfectly, and every mitigation adds complexity, which adds its own failure modes. Electrostatic discharge compounds the radiation problem. Martian dust carries electric charge. As dust accumulates on exterior surfaces, as it infiltrates cable runs and connector housings, as it settles on exposed circuit board edges in unpressurized equipment bays, it creates conditions for electrostatic discharge events. A single discharge across a sensitive circuit can produce the same effect as a radiation strike: corrupted data, false readings, or permanent component damage. On Earth, electronics are protected from electrostatic discharge through grounding, humidity control, and anti-static handling procedures. On Mars, the air inside the habitat is drier than any terrestrial desert, and the exterior environment is a generator of static charge on a planetary scale. The computing systems that monitor the habitat are therefore under continuous assault from 2 directions: radiation from above and electrostatic dust from below. The crew depends on these systems to detect anomalies, regulate life support, manage power distribution, and provide early warning of failures. If the monitoring systems themselves degrade undetected, the crew loses situational awareness without knowing they have lost it. They believe their instruments. Their instruments are lying, not through malice, but through the accumulated damage of operating in an environment that erodes electronic reliability one particle at a time. This is perhaps the most unsettling dimension of first-year survival on Mars. The crew can see dust, they can feel cold, they can measure radiation with dosimeters, they can diagnose mechanical failures through inspection. But electronic degradation is invisible until it produces a consequence, and by the time the consequence appears, the root cause may have been accumulating for weeks or months. Catching it requires the crew to maintain a baseline skepticism toward their own instruments, cross-checking readings, running manual verifications, trusting their physical senses alongside their digital systems. No amount of pre-mission testing can fully prepare the crew for this particular challenge, because no ground test facility can replicate the specific combination of radiation spectrum, dust composition, thermal cycling, and operational duration that the electronics will experience on Mars. The computing systems aboard the habitat will, like every other system, be flight tested for the first time during the mission itself, and the crew will be the ones who discover whether the software that manages their air, their heat, and their water can be trusted after 6 months of continuous operation in an environment it was never fully designed for. On the International Space Station, equipment failures occur regularly. Pumps fail, fans seize, circuit boards malfunction, valves stick. The station maintains an extensive inventory of spare parts and can request specific replacement components on the next scheduled cargo vehicle. Even so, some failures have required multiple extravehicular activities and months of troubleshooting to resolve. The station's environmental control system alone has experienced numerous component failures requiring replacement of major assemblies. On Mars, the spare parts inventory is fixed at whatever was included in the original manifest and the pre-deployed cargo. If a pump model that was expected to last 2 years fails at 7 months, the crew installs the backup. If the backup fails at 14 months, the crew must improvise. They must cannibalize parts from other systems, fabricate replacements from raw materials if a workshop capability exists, or redesign their operations to function without that pump. Every improvisation introduces risk. Every workaround trades performance in one system for survival in another. Every exterior task the crew performs passes through a single bottleneck that is itself a life support system. The extravehicular activity suit. The suit is not clothing. It is a pressurized spacecraft shaped like a human body. It maintains an internal atmosphere, regulates temperature, removes carbon dioxide from exhaled breath, supplies oxygen, manages humidity, protects against micrometeorite impact, shields against a fraction of incoming radiation, and provides mobility across terrain that was never designed for walking. It must do all of this for hours at a time, in temperatures that swing from -20 to -90 degrees Celsius depending on whether the crew member is in sunlight or shadow, while resisting the constant abrasion of the finest and most chemically hostile dust in the explored solar system. On Earth, spacesuit design involves deep trade-offs between mobility and protection. A suit, pressurized to the same level as a habitat interior, would be so rigid that the crew member could barely move. Bending an arm against the internal pressure of a fully inflated suit requires enormous effort. To allow useful mobility, extravehicular activity suits typically operate at significantly lower internal pressures than the habitat, often around 30 kilopascals compared to the habitat's 70. This pressure differential means the crew member must pre-breathe pure oxygen before exiting the airlock, purging dissolved nitrogen from their blood to reduce the risk of decompression sickness. Decompression sickness is not a theoretical concern. It is a physiological hazard documented across decades of diving and aviation medicine. Rapid reduction in ambient pressure causes dissolved nitrogen to form bubbles in blood and tissue. Mild cases produce joint pain. Severe cases cause neurological damage, paralysis, or death. The pre-breathing protocol reduces this risk but does not eliminate it. On Mars, where the crew must perform frequent extravehicular activities throughout the surface stay, the cumulative exposure to pressure cycling between habitat and suit creates an ongoing decompression risk that increases with every excursion. Each extravehicular activity physically exhausts the crew member wearing the suit. Working inside a pressurized garment against the resistance of its joints, seals, and gloves consumes enormous metabolic energy. Studies of International Space Station extravehicular activities show that astronauts burn calories at rates comparable to sustained vigorous exercise on Earth. Heart rates remain elevated for the duration. Core body temperature rises. Sweat accumulates inside the suit because evaporative cooling works differently in an enclosed pressure garment. A crew member returning from a 6-hour exterior maintenance task is depleted in ways that require significant recovery time before they are operationally effective again. On the International Space Station, extravehicular activities are scheduled months apart because they are physically taxing and logistically complex, each requiring hours of preparation and post-activity maintenance. On Mars, exterior tasks cannot be scheduled months apart. Equipment inspections, solar panel cleaning, drilling operations, cable connections, antenna adjustments, regolith sampling, radiation shield construction, and a dozen other tasks require regular presence outside the habitat. The crew may need to perform extravehicular activities multiple times per week, each time accepting the physical cost, the decompression risk, and the suit degradation that comes with every excursion. Because the suit degrades with every use, the joints that allow arm and leg movement rely on bearing surfaces, rolling convolutes, and cable mechanisms that wear under repeated cycling. The visor that protects the crew member's face from ultraviolet radiation and micrometeorite impact accumulates scratches from Martian dust with every exposure. The outer fabric layer, designed to resist abrasion and thermal extremes, frays at stress points. The gloves, the most complex and most failure-prone component of the entire suit, lose tactile sensitivity and develop stiffness as their internal bladder layers fatigue and their exterior coating erodes. Apollo astronauts reported significant glove degradation during their brief lunar surface excursions. Some returned with gloves worn nearly through the outer layer after only a few hours of activity. Martian dust is finer and more abrasive than lunar regolith, and the first-year crew will spend orders of magnitude more time in their suits than any Apollo crew member did. Glove replacements are finite. When the last spare pair is installed, every subsequent excursion carries the risk of a glove breach that exposes the crew member's hand to the near vacuum and extreme cold of the Martian surface. Suit maintenance consumes crew time that competes directly with every other operational demand. After each extravehicular activity, the suit must be inspected, cleaned, and serviced. Dust must be removed from joints and seals. Filters must be checked. Oxygen and carbon dioxide levels in the portable life support system must be verified. Batteries must be recharged. Cooling water must be replaced. This maintenance is not optional. A suit sent outside without proper servicing is a suit more likely to fail, and a suit failure outside the habitat airlock is an event the crew may not survive. The suit also carries the consequences of every excursion back into the maintenance cycle. Dust that embeds in bearing surfaces and joint mechanisms during exterior work does not simply fall off when the crew member returns to the airlock. It remains, grinding against moving parts with every subsequent use, accelerating the wear that will eventually force a component replacement the manifest may not have anticipated. Cleaning a suit after each excursion is not a quick wipe down. It requires systematic disassembly of accessible joints, inspection under magnification, removal of particles from sealing surfaces, and verification that no abrasive residue remains in areas where a single grain of grit could cause a pressure-critical failure on the next outing. This maintenance adds hours to every extravehicular cycle, hours that come directly out of the crew's operational schedule and cannot be skipped without accepting accelerated suit degradation. If a suit develops a critical malfunction during an extravehicular activity, the crew member must return to the airlock immediately. On the International Space Station, the airlock is meters away. On Mars, the crew member may be hundreds of meters from the habitat, working on surface equipment or conducting a geological traverse. The time required to traverse that distance in a compromised suit, depending on the nature of the failure, may exceed the time the suit can sustain the crew member. A small puncture in the outer pressure bladder begins leaking atmosphere immediately. The suit's emergency oxygen supply provides minutes, not hours, of additional survivability. Distance from the airlock becomes the difference between a close call and a fatality. The suits, in summary, are simultaneously indispensable and fragile. They enable every exterior operation the settlement depends on. They degrade with every use. They cannot be manufactured on Mars. They import contamination into the habitat every time they return, and they are carried by a crew that is already physically compromised from 7 months of microgravity transit. The suit inventory is one of the hardest constraints on first-year operations, because when the suits can no longer safely support extravehicular activity, the crew loses the ability to maintain the exterior systems that keep the interior systems running. Medical emergencies magnify every other problem. On Earth, a broken bone is treated in an emergency room by trained orthopedic specialists with imaging equipment, surgical tools, anesthesia, sterile operating facilities, and a pharmacy stocked with thousands of medications. On Mars, a broken bone is treated by crew members who received medical training as one component of their mission preparation, using whatever portable medical equipment fits within the mass and volume constraints of the cargo manifest. A kidney stone, one of the most common medical emergencies in spaceflight due to calcium metabolism changes in altered gravity, can be debilitating. On Earth, it is treatable with pain management, hydration, and if necessary, outpatient lithotripsy. On Mars, the crew has limited analgesics, limited fluid reserves, and no lithotripsy equipment. The affected crew member suffers through it while the rest of the crew absorbs their workload, stretching an already thin operational margin thinner. A dental abscess, a laceration requiring sutures, an allergic reaction to accumulated dust exposure, a cardiac arrhythmia triggered by stress and radiation. Any of these events would be manageable on Earth with access to appropriate medical care. On Mars, each one is a crisis that draws resources away from settlement operations and cannot be referred to a specialist. The crew is their own hospital. Trying to manage a serious medical event through time-delayed communication with a flight surgeon on Earth is like a surgeon attempting to operate by written correspondence, each instruction arriving minutes after the situation has changed. If a crew member becomes incapacitated, the operational impact compounds immediately. A 4-person crew operating at maximum efficiency has no surplus labor. Every person carries a full schedule of maintenance, monitoring, scientific work, and operational tasks. Lose one person to injury or illness, and 25% of the settlement's workforce disappears. The remaining 3 must absorb that workload while also caring for the injured crew member, while also maintaining their own physical and mental health, while also managing every system aboard the habitat that does not pause for human emergencies. If a crew member dies, the psychological impact could threaten the entire mission. The remaining crew must continue operating in a confined space alongside the reality of a death that cannot be addressed with funeral arrangements, grief counselling, or the presence of family. The body must be managed in a habitat with limited storage and no established protocol for remains handling on another planet. The mission continues. Mars does not offer bereavement leave. The psychological weight of all this accumulates in ways that no simulation on Earth has fully captured. The Mars 500 experiment, conducted in Moscow between 2010 and 2011, confined 6 male volunteers in a 550 cubic meter chamber for 520 days to simulate a round-trip Mars mission. The study revealed significant inter-individual variation in psychological responses. 2 of the 6 crew members accounted for 85% of perceived conflicts. 1 developed persistent insomnia that degraded his cognitive performance throughout the mission. Sleep-wake cycles drifted in multiple participants, but Mars 500 was a simulation. The participants knew they were on Earth. They knew that in a genuine emergency, the chamber door would open. They knew that the air outside was breathable, that hospitals existed nearby, that the experiment would eventually end, and they would walk outside into sunlight and gravity and normalcy. On Mars, there is no chamber door. The emergency exit leads to a near vacuum saturated with toxic dust under a sky that offers no protection from cosmic radiation. The crew cannot quit. They cannot step outside for fresh air. They cannot drive to a different city for a weekend. They are confined to a pressurized volume smaller than a modest apartment, sharing that space with the same 3 or 4 people for 500 days, with a communication delay that makes real-time conversation with anyone on Earth impossible. NASA identifies the risk of behavioral changes and psychiatric disorders as one of the most serious threats to long-duration mission success. Isolation, confinement, prolonged separation from family, communication delays, workload stress, sleep disruption, and the monotony of routine all contribute. On the International Space Station, crew members can video call family with minimal delay, receive care packages, watch live television, and look out the cupola window at a planet that is visually and emotionally still home. They know that a Soyuz or Crew Dragon capsule can return them to Earth within hours. On Mars, Earth is a bright dot in the evening or morning sky, a point of light indistinguishable from the surrounding stars without careful observation. Communication with family consists of recorded messages sent back and forth with delays that make conversation impossible. There are no care packages. There is no fresh food arriving on a resupply vehicle. There is no window view that offers comfort, only an alien desert stretching to a horizon that curves more sharply than Earth's, under a salmon-coloured sky that never looks like home. The psychological literature on polar overwinter cruise, submarine deployments, and space station expeditions all document a phenomenon informally called the third quarter effect, a period roughly 3/4 of the way through a mission when morale drops, irritability increases, and interpersonal tensions peak. For a 500 Sol Mars surface stay, the third quarter would fall somewhere around Sol 350, deep into the Martian winter at some landing sites, when power margins are thinnest and the return window is still months away. And Mars has seasons. The planet's axial tilt is remarkably similar to Earth's, roughly 25 degrees, which means Mars experiences spring, summer, autumn, and winter. But a Martian year is nearly twice as long as an Earth year, so each season stretches across months. Winter at a mid-latitude landing site brings shorter days, lower solar elevation angles, reduce solar power generation, and colder temperatures that increase heating demand. The thermal control system works harder. The power budget tightens. Exterior maintenance becomes more difficult as the crew must operate in colder conditions with less daylight. Winter is also when the risk of major dust storms increases. Martian dust storms are driven by solar heating differentials, and the transition from southern hemisphere spring to summer, which corresponds to the planet's closest approach to the sun, historically correlates with the onset of large regional and occasionally global storms. A major storm arriving during winter at a northern hemisphere landing site would compound every existing stress. Reduced solar power, increased dust accumulation on exterior equipment, reduced visibility for extravehicular activities, increased atmospheric dust infiltration into the habitat, and the psychological burden of watching the sky darken and knowing that no human intervention can control the weather on this planet. The storm could last weeks. During that time, the crew shelters inside the habitat, running life support on reactor power, conserving every resource, cleaning filters more frequently, monitoring atmospheric pressure for anomalies that might indicate a seal breach masked by the storm's effects on sensor readings. They cannot go outside. They cannot inspect the exterior equipment. They cannot clear dust from solar panels or check physical connections on surface hardware. They wait. And while they wait, every system continues aging. The thermal cycles continue. The dust continues accumulating on surfaces the crew cannot reach. The radiation continues its invisible bombardment. The consumables continue diminishing. The calendar continues counting toward a return window that is still months away. This is the slow war, not a single battle but an endless series of small engagements, each one manageable in isolation, each one compounding with the others into a cumulative burden that tests the limits of human endurance and engineering reliability simultaneously. The crew did not come to Mars to fight this war. They came to explore, to discover, to build the first permanent human presence on another planet. But exploration is a luxury that survival must purchase first. Every hour spent replacing a clogged filter is an hour not spent conducting science. Every day spent troubleshooting a water purification malfunction is a day not spent investigating the geology outside the habitat. Every week spent managing a crew member's psychological crisis is a week not spent advancing the mission objectives that justified the billions of dollars and the decade of preparation that brought them here. The first year forces the crew to confront a truth that no mission briefing fully prepares them for. Mars does not care about their mission. Mars does not care about their science objectives, their exploration timeline, their personal ambitions, or their species' dreams of becoming multiplanetary. Mars is a physical environment governed by chemistry, thermodynamics, and orbital mechanics. It corrodes, irradiates, freezes, and suffocates with complete indifference. And the machines keeping the crew alive are in a race they did not choose. They are racing against degradation, against dust, against thermal fatigue, against radiation damage to electronics, against the slow accumulation of perchlorate contamination in systems designed for clean environments, against the statistical certainty that in a complex system operating continuously for 500 days, something will fail in a way that was not predicted, at a time that is not convenient, and in a location that is not easily reached. The crew knows this. They trained for it. They simulated it. They read the failure analyses from every Mars robotic mission that ended prematurely. They studied the emergency procedures from every close call aboard the International Space Station. They practiced repairs in analog habitats on Earth, and possibly on the Moon. But they have never done it here. They have never done it on a planet where the outside air will kill them, where the nearest help is a radio signal that takes 20 minutes to arrive, where the next resupply ship will not launch for another year, and where every sunrise is a reminder that they are the most isolated human beings who have ever lived. The slow war does not end. It does not build to a climax and resolve. It grinds on, sol after sol, through dust and cold and silence, testing every system and every person until the return window finally opens, or until something breaks that cannot be fixed with what remains. The first year is not a chapter in the story of Mars settlement. It is the entire question. Can humans survive long enough, on machines that last long enough, with resources that stretch far enough to reach the point where survival is no longer in doubt? That question has not been answered yet. It will not be answered by simulations or analogues or robotic precursors. It will be answered only by the crew themselves, alone, on Mars, during the first year that decides whether this planet becomes a second home or a monument to ambition that exceeded reach. There is a moment that every engineering team dreads more than catastrophic failure. It is the moment when nothing is visibly wrong, but nothing has been proven right either. The habitat is pressurized. The reactor is generating power. The oxygen system is running. The water extraction rig is producing liters per day. The carbon dioxide scrubbers are cycling. The food supply is being rationed on schedule. The communication link to Earth is active, delayed but functional. Everything appears to work, and that appearance is the most dangerous condition the crew will face during the first year on Mars, because everything on Mars is new. Not new in the way a product fresh from a factory is new, tested against specifications and shipped with a warranty. New in the way a prototype is new, assembled from components that individually pass their tests but have never operated together. In this environment, under these conditions, for this duration. The habitat is a prototype. The life support system is a prototype. The power system is a prototype. The water extraction rig is a prototype. Every piece of the settlement is being flight tested for the first time, and the test pilots live inside the experiment. On Earth, prototype testing follows a structured protocol. Engineers operate the system under controlled conditions, monitor performance, identify failure modes, redesign weak components, and iterate over years. Aircraft engines require thousands of hours before certification. Nuclear reactor designs require decades of regulatory review, simulation, and graduated operational trials. Testing of life support systems for the International Space Station involved years of ground-based operation, followed by gradual integration into the station's existing systems, with the constant option of falling back on proven backup technology or evacuating the crew. On Mars, the testing protocol is the mission. The crew is simultaneously the test team and the test subjects. If a system fails during testing on Earth, the engineers go home and redesign it. If a system fails during its first year on Mars, the crew must fix it, work around it, or accept the consequences. There is no redesign cycle, there is no second prototype, there is no home to go to. This is why the first year is categorically different from every subsequent year of Mars habitation. In the second year, the crew will have 12 months of operational data. They will know which seals degrade fastest, which filters clog first, which mechanical joints require the most maintenance, which electrical connections are most vulnerable to thermal cycling. They will have replaced their first failed component and learned how the replacement performs. They will have survived their first dust storm and measured exactly how much it affected power output, atmospheric contamination, and equipment degradation. They will have calibrated their rationing schedules against actual consumption rates rather than Earth-based estimates. In the third year, the crew or their successors will have a maintenance history. They will know the mean time between failures for critical components under actual Martian conditions. They will have developed improvised repair techniques that work for their specific hardware in their specific environment. They will have routines, muscle memory, institutional knowledge accumulated through lived experience, rather than written procedures. But in the first year, none of that knowledge exists. The crew operates on estimates, simulations, and engineering margins that were calculated using the best available data, which is data collected by robotic missions that operated under fundamentally different conditions. Rovers do not breathe. Orbiters do not need pressurized habitats. Landers do not consume water or produce waste. The data from robotic missions tells the crew a great deal about Martian geology, atmospheric behavior, radiation levels, and surface chemistry. It tells them almost nothing about how human-occupied systems degrade over months of continuous operation on Mars. The margin of error during the first year is therefore at its narrowest when the demands on it are at their highest. The crew is learning the environment, while simultaneously depending on systems that are learning the environment at the same rate. Every surprise the planet delivers, an unexpected dust accumulation pattern, a temperature extreme outside the predicted range, a perchlorate concentration higher than orbital surveys indicated, must be absorbed by systems with no operational history and no performance buffer established through experience. Consider what happens when redundancy has not yet been validated. Mission designers build redundancy into critical systems: 2 oxygen production units, 2 water purification lines, backup power converters, spare communication transmitters. On paper, if the primary system fails, the backup activates and operations continue while the crew repairs the primary unit. This architecture works when both systems have been proven operational, but during the first year the backup has likely never been activated. It was shipped to Mars, deployed, connected, and left in standby mode. It passed its initial checkout. Telemetry shows nominal readings, but it has never run under load. It has never processed actual Martian carbon dioxide or actual perchlorate-contaminated water. The first time the backup is truly tested is the moment the primary fails, which is the worst possible moment to discover that the backup has its own undiscovered problem. This pattern has precedent in spaceflight. The International Space Station has experienced multiple instances where a backup system, presumed functional based on telemetry, failed to perform correctly when activated during an emergency. In some cases, the backup had degraded during storage. In others, it had a manufacturing defect that was never detected because it was never operated under real conditions. The station survived these incidents because resupply was weeks away and crew evacuation was hours away. On Mars, neither option exists during the first year. The crew must therefore prove the backups before they are needed. This means running each redundant system under load, verifying its performance, and confirming it can sustain operations independently. But running backups consumes resources: power, consumables, crew time. Every hour spent testing a backup oxygen unit is an hour that unit is aging. Every test cycle adds wear. The crew faces a dilemma with no clean answer: test the backup and reduce its remaining lifespan, or leave it untested and accept the risk that it might not work when the primary fails. Earth cannot resolve this dilemma in time. A message describing the situation takes up to 22 minutes to reach mission control. The response, after analysis and deliberation, takes up to 22 minutes to return. Multiple exchange cycles might span days. Meanwhile, the decision must be made now, today, on this Sol, by the crew alone. This isolation from Earth support is not merely a communication inconvenience. It is a structural feature of the mission that transforms every operational decision into a survival decision. On the International Space Station, the flight control team in Houston monitors systems 24 hours a day. Multiple controllers watch telemetry streams from every major subsystem simultaneously. When an anomaly appears, the ground team often identifies it before the crew does. They have time to analyze, consult reference documentation, confer with engineering teams at contractor facilities, and develop a response plan before alerting the crew. On Mars, the telemetry that reaches Earth is already minutes old by the time it arrives. An anomaly detected by Houston occurred in the Martian past. The response Houston develops is based on a situation that has already evolved. By the time the crew receives guidance, the system in question has continued operating, degrading, or failing for the duration of the round-trip communication delay, plus the analysis time on the ground. The crew may have already taken action based on their own assessment, action that may or may not align with Houston's recommendation. Over time, this dynamic shifts the locus of decision-making from Earth to Mars, not by policy but by physics. The crew becomes the primary authority on their own survival, because they are the only people who can observe, diagnose, and respond to problems in real time. Mission Control becomes an advisory body, valuable for long-term planning, engineering analysis, and psychological support, but unable to function as the immediate decision-maker in time-critical situations. This shift has psychological consequences that compound the isolation. The crew must internalize the reality that they are responsible for their own survival in a way that no previous space crew has experienced. Apollo astronauts knew that Houston was listening in real time. Station crews know that the ground team is watching around the clock. Mars crews know that they are alone in the only way that matters. Alone in the present moment, where decisions must be made and actions must be taken. Launch window mechanics impose a structural timeline on the first year that intensifies every other pressure. The crew landed on Mars during a specific window dictated by planetary alignment. The next return window opens approximately 500 days later. Between landing and that window, the crew is on Mars regardless of what happens. If the habitat suffers a major depressurization on Sol 40, the crew cannot leave on Sol 41. If the reactor fails catastrophically on Sol 100, the crew must survive on backup power for 400 more days. If a crew member develops a medical condition that requires treatment only available on Earth, that treatment is 500 days and a 7-month flight away. This is not a theoretical concern. It is the defining constraint of the first year. Every other challenge, dust, radiation, equipment degradation, psychological stress, resource depletion, derives its severity from the fact that the crew cannot leave. On Earth, when a building becomes uninhabitable, the occupants evacuate. On the International Space Station, when a module loses pressure, the crew seals the hatch and retreats to another module, and if the entire station becomes untenable, evacuation is measured in hours, not months. On Mars, the crew has no other building, no other module, no return vehicle capable of immediate departure. The habitat is it. If the habitat fails, the crew has only what remains functional, whatever that turns out to be. And yet, the crew must also prepare for departure. The return flight requires propellant, and the most likely mission architecture relies on in situ resource utilization to produce at least some of that propellant on Mars. The Sabatier reaction combines carbon dioxide from the Martian atmosphere with hydrogen to produce methane and water. The methane serves as fuel. The water can be electrolyzed to produce oxygen for the oxidizer, and additional hydrogen to feed back into the cycle. This process, if it works at scale, dramatically reduces the amount of propellant that must be launched from Earth, making the mission architecturally feasible. But the propellant production plant is another system that must operate continuously on Mars, drawing power, consuming resources, and requiring maintenance throughout the surface stay. If it underperforms, the crew might not have enough propellant to leave when the return window opens. If it fails entirely, the crew is stranded until a resupply mission can deliver propellant, which means waiting for the next launch window, the next transit, the next landing. That could add 2 or more years to their stay, years for which they were not provisioned. The propellant production timeline is therefore a countdown running alongside every other countdown. The crew must simultaneously keep themselves alive, maintain the habitat, manage their health, conduct their mission objectives, and produce enough fuel to leave. These demands compete for the same finite resources: power, crew time, equipment capacity, and water. A water system failure does not merely threaten the crew's drinking supply, it threatens the propellant production chain. An oxygen system malfunction does not merely threaten breathing air, it threatens the oxidizer stockpile for the return vehicle. Everything connects, everything competes, and during the first year, none of these interconnected systems has demonstrated that it can sustain its share of the load for the full duration required. There is a concept in reliability engineering called the bathtub curve. It describes the failure rate of complex systems over their operational lifetime. Failures are most frequent at the beginning of a system's life, when manufacturing defects, installation errors, and design weaknesses reveal themselves under actual operating conditions. This period is called infant mortality. Failure rates then decrease and stabilize during the system's useful life, as the weak components have been identified and replaced. Eventually, failure rates rise again during the wear-out phase, as aging and degradation take their cumulative toll. The first year on Mars places the entire settlement squarely in the infant mortality phase. Every system is new. Every component is untested in its actual operating environment. The failure rate will be at its highest precisely when the crew has the least operational experience and the fewest established workarounds. As the months progress, the crew will discover and address infant mortality failures, replacing weak components, adjusting procedures, learning the real behavior of their equipment. The failure rate will begin to decrease. The settlement will begin to stabilize. But that stabilization only happens if the crew survives the infant mortality phase. And that phase is defined by the concentration of unknowns, unknown failure modes, unknown environmental interactions, unknown system behaviors that only manifest under sustained real-world operation. The crew must navigate a landscape of unknowns, with finite resources and no external rescue, learning as they go, adapting as they must, absorbing failures as they come. If they succeed, something profound happens. The settlement transitions from a crisis to a routine. Systems that survived 6 months will likely survive 12. Components that performed through the first dust storm will likely perform through the second. The crew develops confidence grounded in evidence rather than hope. Maintenance schedules replace emergency repairs. Consumption rates stabilize. The oxygen system produces reliably. The water system delivers consistently. The reactor hums along, unremarkable in its steadiness. This transition, from survival to routine, is the actual founding moment of a Mars settlement. Not the landing, not the first footprint, not the flag ceremony. The moment the settlement is truly founded is the moment survival becomes boring. The moment when the crew wakes up, runs their morning systems check, notes that everything is nominal, and feels no particular anxiety about it. The moment when a minor equipment alert does not trigger adrenaline because the crew has seen that alert before, knows what causes it, and knows how to resolve it. The moment when the daily rhythm of maintenance, monitoring, and operation feels familiar rather than frightening. That moment cannot be designed. It cannot be scheduled. It cannot be mandated by mission control or guaranteed by engineering margins. It can only be earned, soul by soul, repair by repair, storm by storm, through the accumulation of operational experience that no simulation can provide. And here is the truth that the first year forces humanity to confront. Reaching Mars is an engineering problem. It is extraordinarily difficult, but it is a problem with defined parameters, delta-V budgets, trajectory calculations, heat shield designs, propulsion systems. We know how to frame it, even if we have not yet solved every detail. Landing on Mars is a harder engineering problem, but still fundamentally tractable. It requires innovations in entry, descent, and landing that are being actively developed. And while the challenge is severe, the physics is understood. But surviving the first year on Mars is not purely an engineering problem. It is an endurance problem. It is a problem of human beings operating imperfect machines in an unforgiving environment for a duration that exceeds anything they have personally experienced, with consequences for failure that exceed anything previous space crews have faced. It is a problem that tests not just hardware and software, but judgment, resilience, creativity, discipline, and the ability to remain functional under sustained stress with no prospect of relief. The machines must work. That is necessary, but it is not sufficient. The people must also work. They must work together in a confined space for 500 days. They must trust each other's competence during emergencies they did not predict. They must manage conflict without the option of physical distance. They must maintain morale through months of monotony, punctuated by moments of genuine danger. They must resist the psychological erosion of knowing that they are farther from help than any human being has ever been. Mars does not become dangerous only because it is alien. Any crew member can recite the statistics about atmospheric pressure, surface temperature, and radiation levels. They trained for years knowing these facts. Mars becomes dangerous because the first year is when the settlement is weakest, when every system is newest, when every margin is thinnest, when every failure is the first of its kind, and when the crew has not yet developed the lived expertise that transforms a collection of machines into a functioning home. The difference between a planned base and a base that actually works is the difference between a blueprint and a building that has weathered its first winter. The blueprint contains every specification, every tolerance, every design intention, but the blueprint cannot predict which wall will leak, which pipe will freeze, which door will jam. Only the winter reveals those answers, and only the people who live through the winter can apply what it teaches. The first crew on Mars will live through the Martian equivalent of that winter. They will discover which systems fail first, which procedures need rewriting, which assumptions were wrong, and which margins were too thin. Plus, they will patch, adapt, improvise, and endure. And if they succeed, if they reach the end of the first year with the habitat intact, the life support running, the crew healthy enough to continue, and the propellant supply sufficient for return, they will have accomplished something that changes the trajectory of human civilization. Not because they planted a flag, not because they collected samples, not because they proved that humans can reach Mars. We will know that before they land. They will have proved that humans can stay, that a human settlement on another planet can survive its most vulnerable phase, that the machines can last, that the people can endure, that the gap between arrival and routine can be crossed, and they will have done it alone, on a planet that offered nothing, in a habitat that started as a prototype and ended as a home, through a year that no one on Earth fully understood because no one on Earth has ever lived it. The sun rises over the Martian horizon, pale and distant, casting long shadows across a landscape that has been touched now by human hands. The habitat stands where it landed, surrounded by tracks in the regolith, by equipment deployed and maintained and repaired and deployed again. The reactor hums, the oxygen system runs, the water system produces, the air inside smells of recycled metal and polymer and something faintly human, the accumulated presence of people living where no person has ever lived. The crew runs their morning systems check. Pressure holding, temperature stable, oxygen nominal, carbon dioxide scrubbers functional, water reserves sufficient, power output steady, communications operational. Everything is working. And for the first time, that sentence does not carry an unspoken asterisk. It does not mean everything is working so far, or everything is working but we do not know for how long. It means the systems have proven themselves through months of continuous operation. It means the crew has learned their equipment, learned their environment, learned each other. It means the settlement has survived its infancy. Outside, the Martian wind pushes fine dust across a plain that stretches to the curved horizon. The sky is the colour of a fading bruise, salmon and ochre and pale amber. Earth is somewhere in that sky, a point of light that the crew has not seen with unaided eyes in months because the geometry of orbits has placed it behind the sun. They are alone. They have been alone since they landed. They will be alone until the return window opens or the next crew arrives. But the habitat holds, the air holds, the water holds. The machines keep running because the crew keeps them running. Because every repair made during the first year bought another week of operation. Because every improvised fix taught the crew something no training could teach. Because every crisis survived became evidence that the next crisis could be survived too. Mars did not become a home the moment humans arrived. It did not become a home when the flag was planted, or the first rock was collected, or the first message was sent back to Earth. Mars became a home the way every home becomes a home. Slowly. Through difficulty. Through the accumulation of small victories that eventually outweigh the daily struggle of staying alive. The hardest part of Mars was never getting there. It was the first year after arrival, when nothing was routine, when nothing was proven, when every system was still earning the right to be trusted, and when the crew had nothing to rely on except their training, their tools, and each other. The first year is over. The settlement stands. And for the first time since the crew touched down on this cold, silent, indifferent world, survival has become boring. That is when Mars becomes a home. Not with a celebration, not with a declaration, with a morning systems check that reveals nothing unusual, on a soul that feels like every other soul, in a habitat that has quietly, stubbornly, against every odd this planet could impose, become the place where human beings live.